Hi, in this video we'll go over modeling with UML. Specifically we'll look at state diagrams. UML stands for Unified Modeling Language, and in the previous videos we looked at use case diagrams and class diagrams. Today we'll look at a dynamic modeling diagram called state diagram. So the idea here is to model the behavior of the system, and this is in response to certain events. These events can be either external or internal triggers. So we want to be able to model how the system responds to these external stimuli. So here we are specifically concerned about a single object and the different states that it can be in based on these external stimuli. So the notation is still the graph-based notation, just like in other UML diagrams, wherein there's nodes which represent the different states of the system or the object, and then the events are the edges between the nodes. And whenever the event occurs, the idea is that the system moves from one state to another state. So there's directed edges between the nodes. Now state diagrams are an integral part of UML. They're an important part of UML because they're able to depict this dynamic behavior of the system. So we'll use the example of a microwave oven and show the state diagram for it. Microwave oven, we're all familiar with it. We use it in our day-to-day lives, and we look at the different states that it can be in. So you see a graph-based notation over here. Here are the nodes that are representing the different states that the microwave can be in. The top portion of the node is displaying the name of the state. So the first state there is a waiting state. So the microwave is in a waiting state. Now the portion below the title of the state is in optional actions. So any kind of actions that are happening in that state can be listed over there, and it's optional. So in the waiting state, basically all it's doing is displaying the time. That's what it says. Our second state here is a full power state. So the action over there is that the power is set to 600. So similarly, there are other states like half power, set time, disabled, enabled, and so on. Now typically in a state diagram, we always need to indicate what is our start state, the initial state, and what is the final state. Now sometimes it could be possible that there is no final state because it's always continually doing something, and that's fine if that's the case. So the start state is represented using the solid circle, as you can see over here. So our start state in this case is waiting. Now the final state is indicated using these two concentric circles with the center one indicated as solid. So our final state in this case is the waiting state again. So here this is one of those examples where the final state is in fact the starting state itself, and that's fine. So we can indicate it that way, or just have this instead of repeating the waiting state here, you can have the arrow go back to the initial state. So then we see that there's these directed arcs or edges that are connecting the different nodes, and on top of the arc or the edge there is a label indicating what the event or trigger is. So the microwave oven goes from a waiting state to a full power state on the trigger full power. So if the button full power is pressed, that's when the state changes from waiting to full power. So similarly, you see all of the other triggers. When half power is pressed, it moves to half power. When the timer is pressed, it moves to set time. From set time, if the door is opened, then it goes into a disabled state. If the door is closed, it goes back into an enabled state. From the disabled state, if the door is closed, it goes into an enabled state, and so on. So when the microwave is in full power, one can click the half power button and take it to the half power state. from half power it could go into full power state. So basically, as you can see from the diagram, the idea is to think of one particular system or object and all of the different states that it can be in, and what are those internal or external triggers or stimuli that can cause it to go from one state to another. That's the idea, and typically this is done for a system or a subsystem that's particularly complex, or usually a single object that's particularly complex and hard to understand. So coming up with this kind of a state diagram helps deal with that complexity of that object and better understand it. So there could be a situation where say set time, and clicking on the number takes it back to set time. So clicking on the numbers will keep it in that set time state until something else is clicked, and the time gets set and we move on into another state. Say for example, you're setting the time, and then from there the door is opened, then the state changes into a disabled state, and so on. So from the enabled state, when the start button is clicked, then it starts, it goes into operation. From there one can hit cancel and get it back into waiting state, or open the door and get it into a disabled state, and so on. So the idea is to be exhaustive and think of all of the possible states that this microwave can be in, and that helps in designing and then later on implementing that particular object, knowing all of the different states that it can be in. So as you can see, the different states were the nodes. So waiting, half power, full power, set time, disabled, enabled, all of these were the different states for the microwave oven. And then the stimuli were those directed edges. So either pressing half power or full power or timer, each of these were the triggers that were causing a state change. So here's another example. And this is the example of life of a PhD candidate. So the different states that the candidate would be in during the entire program. So again, the start state in this case, they start over here with taking classes. So that's the very first state. When the student passes all classes, then they get into a state of taking the qualifying exam. When the student passes that, they get into writing a survey, followed by a candidacy exam. Passing that will take them into a topic defense. So as you can see, from any of these states, if either the student decides to quit or if the student fails, then they get into this final state. Now there could be two final states, and that's also okay in state diagrams. There could be multiple final states. So there's a final state here which is a result of quitting or failure, or there is a final state here which is a result of successfully passing and completing the program. Now another thing that we notice here is a way of packaging multiple states into one. So there is this larger state called all but dissertation. So basically the student has completed all of the other requirements. The only thing left is writing the dissertation and the final defense of the dissertation. So that's this all but dissertation state. But within that state, there's multiple substates, and those multiple substates are, say, writing the dissertation, and then from there, once a student gets a job, then the final defense. Typically, students would wait on getting a job before they have their final defense and then graduate. So there's these substates. So that's another way in which the state diagrams could be organized. There could be a larger state with substates within it. So as you can see, the actions part of it is optional. That's the reason in this case there's no actions defined. There's just the state name that's specified. But what is required is this start state, having the state name within the nodes, and then all of the directed edges must have a label indicating the trigger. So in this case it's passed. That trigger must be specified to it because that's what's causing the state to change. Here's another example of a seminar search. So say you're on a web page where the goal is to look for a seminar, and if you find one that you're interested in, you make a reservation for it. So again, we start with this initial state. Our first state is ready to search. So from there, the search text is entered that causes the state to change to showing the program's list, the list of all of the seminars. From there, the user selects one to see, and then the detail page shows up. So that's the next state. From the detail page, it goes into, if the person decides to make a booking, then it goes into the booking state. Now at the booking state, now there could be some conditions, additional conditions that can be added. From the booking state, we want to check if the user is already logged in. If yes, then the program, the seminar is booked, so is in this booked state, and that's our end state as well, the final state. But if the person is not logged in, then the user is asked to log in. If he logs in, then it goes back to the detail page, and from there the user can perform the booking and get to the final state. If the user decides to not log in, then from there the user is basically taken to the final state or the end state. So another example, another way to represent states, again, as you can see here, only the state names are specified. There's directed edges with labels. There's a start state, end state. The new thing that you see is these conditionals, and based on the outcome of the condition, whether if it's a yes or a no, or a true or a false, or any other additional conditions, based on that outcome, we can have multiple paths in the graph. So that's a state diagram. Let's try out an exercise with a simple specification of what's called a simple watch. So basically, the simple watch has an LCD display to display the time in hours, minutes, and seconds, and then it has two buttons, 1 and 2 push buttons. The purpose of the buttons is pressing the first button will make the hours blink so that it can be set, and then the second button can be used. Pressing the second button will increment the hours. Now if we repeatedly press the first button, say when the hours is blinking, if you press button 1 again, that will stop blinking hours and make the minutes blink, and then from there 2 can be used to increment the minutes. Now when the minutes is blinking again, if we press button 1, that will make the seconds blink. Now when seconds is blinking, if you press button 1 again, that will take it back to hours blinking. So basically 1 is used to select whether we want to set time for the hour part, the minute part, or the seconds part, and the second button is used to increment the number that's blinking. And then when you're done finally setting the time, basically press both 1 and 2 buttons together, and that will set the time. So say that's the behavior of this simple watch, and we need to draw a state diagram to model it. So here now we're thinking of all of the different states that this watch can be in, and what are the triggers that's going to cause the state to change. So let's look at the diagram. So basically here's our start state. We start there. From the start state, which is basically the watch and the LCD display being shown, if button 1 is pressed, then we go into the blink hours state. From there, if button 1 is pressed again, then we go into blink minutes. Button 1 is pressed again, we get into blink seconds. And from there, if both button 1 and 2 are pressed, goes into stop blinking and into the final state. Now from any of these 3 blink states, if button 2 is pressed, then that results in incrementing that particular part. So it's either the hours or the minutes or the seconds, and then it'll increment and take it back into the blink state. From any of these blink states, if both buttons 1 and 2 are pressed together, then that's when it goes into stop blinking and into the final state. So basically that shows the complete operation. On every state we look at all possible actions that could be taken. So at blink hours, what are the different possibilities? Could press button 1, what happens then? Could press button 2, what happens then? Or you could press both button 1 and 2, so what happens in that case? So in that way, you think about all of the states and all of the different actions that are possible and what kind of state changes happen in each of those cases. And that's what's drawn through the state diagram. And again, like I said, it's the purpose of this diagram is to understand the behavior of one particular object, a single object, and the different states that it can be in. And we don't do this for every object in the system. It's typically done for any particularly complex object that's very dynamic in its behavior, and to better understand that dynamic behavior. So so that's the basic notation for state diagram. And the purpose is to represent the dynamic behavior. In the follow-on videos, we'll look at activity diagrams, which is also used for representing dynamic behavior. Thank you.